We can start adding people whenever you are ready.
Yeah, it looks like we're almost at the top of the hour. So why don't you open the door, let them in?
Sounds good.
Well, greetings, everybody. It's 1 o'clock. Welcome to the second lecture in our series on the cosmos. And today we're going to focus on the early universe. We covered some of this last time, but we did it in a rather superficial way because we were in the business last week of talking about everything that's going to be presented in the class. Today, we're going to do a deep dive into the early universe, and here we go. Yeah, I guess we're going to have one quick detour, and that is answer last week's questions. And we did get a question, isn't there a law of uniformity in all directions? Well, it's not a law, it's an assumption. And the words that the professional use is they assume the universe on a large scale, a scale of about 300 million light years, is that the universe is isotropic and homogeneous. So here's a little way to depict this. Homogeneity means it's the same everywhere. But the isotropic term refers to whether it's the same looking in all directions. So this illustrates isotropy, looks the same in all directions, but it's not homogeneous because some places the lines are farther apart and here they're closer together and so forth. But that's an assumption. And the science of today has no method for proving that that assumption is true. It turns out it's very likely to be true on this scale and larger scales than this because we have various competing experimental evidence, observations that agree with our model of the universe, the so-called Friedmann model, and but we can't prove that. Next question is, I said that the universe is around 90 billion light years in size, but it's only 13.8 billion years old. And the reason is that in the very early universe, the expansion rate of the universe was much higher than it is now. It's still high enough that the most distant objects are receding from us at faster than the speed of light. And the result is this is the curve we get from using observational data about the amount of matter and dark energy and so forth in the universe, and what's called the look back distance. That is, if we look towards the early universe using the parameter z, that's what this has, the parameter z to it. Look at this curve. The curve says if we look back to the earliest time, which is back here, right after the Big Bang, here's the distance to that surface, that the cosmic microwave background, and it's more than 44 billion light years away now. I mean, it's a difficult thing to describe the size of the universe because the universe has been expanding all this time, and the impact has been the most distant object, the cosmic microwave background, has continued to run away from us at, as I say, more than the speed of light. Okay, asteroids, how do they fit into gravity versus expansion? There's no connection. Asteroids are a local property of our solar system, and our solar system, I think you appreciate, is a tiny, tiny spot in the Milky Way. The expansion of the universe is measured on a scale of, well, we have it here, millions of light years. And so there's no connection between asteroids, just lumps of rock and ice floating around in our solar system, is unrelated to the expansion of the universe. Could cold dark matter and energy discoveries alter our estimates of the age of the universe? Well, sure. But we have multiple ways to measure the age of the universe since the Big Bang, and they agree that it's this number like 13.8 billion years. And it's unlikely that any future description of the why dark energy and dark matter exist would change that number. It's possible, but seems unlikely. Well, let's move on to this week, the early universe. And here are the key things we got from last week. We have these issues related to the expansion of the universe and the accelerating expansion, the fact that the universe has a flat geometry, that virtually all the atomic matter in the universe was made in the Big Bang, that's hydrogen and helium. The rest of it was made in stars. The fact that we also learned the fact that only about 5% of the energy in the universe is in the form of the atoms that we are made of and that stars and planets are made of. We also pointed out the universe is vastly bigger than the part we can see, because we can only see our observable universe. Others far away from us will see a different observable universe. And so if you could aggregate the volume space that all observers have, you'd find the universe is vastly bigger than the numbers I've been pointing out to you. And the last thing we talked about was the fact that we're made up of star stuff. That comes from the fact that the periodic table is dominated by hydrogen and helium made in the Big Bang, but other elements created in stars, and they are in us. So to summarize, there is structure to the universe. We saw that in the form of the clusters of galaxies, how they gather together under the influence of gravity. Expansion is accelerating. We know the geometry. The chemistry of the early universe is well established using the laws of nuclear physics. We can explain how various types of stars create elements. And we have these unexplained properties of the universe of dark energy and dark matter that are propelling a lot of research. So Big Bang nucleosynthesis, and I abbreviate it as BBN, predicts the concentration of atomic matter that we observe when we look at galaxies and their composition. That's a fantastic source of information about the early universe, because if our understanding of the laws of nuclear physics were wrong, we wouldn't be able to predict how much of different elements appear in the galaxies in our universe. We also, to understand the early universe, we exploit the cosmic microwave background, and we'll talk about that quite a bit today. This is the earliest light that we have from the evolution of the universe. This is light as it existed 300 to 400,000 years after the Big Bang. We have no light prior to that we can use for scientific purposes. There is research being done using gravitational waves as a possible source of information about the very early universe, but right now this is the biggest source of information that we have. The James Webb Space Telescope, of course, is just about 3 years old, and it has added tremendously to our understanding of the universe, the early universe, because it operates in the infrared spectrum. And remember, we talked about redshift the light from ancient galaxies is redshifted into the infrared frequencies of the light we see today. So using, for example, the wavelengths that humans are sensitive to, just everyday red, green, blue light, doesn't show us light from the early universe as well as using infrared from the early universe, because all that light, whether it's X-rays or even more energetic light, has been redshifted over the lifetime of the universe to the wavelengths that the Webb telescope was designed to detect. We'll go into that. And Hubble, we're also going to compare James Webb to the Hubble Space Telescope, which sees just into the infrared, but not nearly as well as James Webb. I will explain why that's so. One of the other advantages of James Webb is that when we look at a galaxy, here's an image of the star-forming region in what's called the pillars of creation. You notice here we can't see these areas of intense collections of dust and gas. This is wavelengths seen by the Hubble Space Telescope, and you can always pick out an image from Hubble because it'll have this cross here that reveals the design of the telescope. James Webb, on the other hand, has a 6-spike display, but you can see, compare right here and right here, we can see through the gas and dust in the infrared spectrum in a way that we cannot in the visible spectrum. And the reason this happens is something we've all experienced. If you're driving through fog, you're driving through a cloud that's on the ground, and the droplets of water are very tiny, and they scatter light so efficiently that you cannot form images. You can just barely, intense fog, you can only see your hand in front of your face. But if you're driving through the same amount of water in the atmosphere, but it's in the form of rain, which are much larger droplets, you can see through a rainstorm. These small droplets scatter more efficiently. And that's true in astronomical observation as well. The dust that's present in these images here in the case of Hubble is much more efficient at scattering. But if you go to longer wavelengths, you can see right through and see the stars in the background. So here's the familiar history of the universe in one drawing from the Big Bang. We have this period here where we have what's called inflation, and we'll try to have time to talk about the properties of inflation in this lecture. And then we have the universe cool enough that atoms can form and the universe becomes transparent. That's when we have this sphere of light around us called the cosmic microwave background. At that point, that light was able to propagate to us, and we see it today using the proper instrumentation that operates in the microwave spectrum. But that was before there were stars. And we went roughly 400 million years with no light in the universe because there were no stars. All that was around was the glow of the original Big Bang. And finally, stars formed and collected in clusters we call galaxies, and the rest of the universe is just the evolution of those galaxies gathering under the influence of dark matter. We'll talk about that as well. So we have this traditional view of the roughly 14 billion years of the universe, and it's described here in words. This is the early universe we're going to talk about today. One way to talk about it is to look at the temperature history. And using Einstein's theory of gravity and other evidence, we get curves like this. This is the temperature as a function of time. Temperature, notice these are very large, high temperatures. Here's 1 degree, 10 to the 10th, that's 10 billion degrees, and so forth. And in the very early universe, we have extremely high temperatures. That's the time at which atoms could not form. And temperature here, we're talking about the energy of the light present in the universe. So in the early times, these very short times, 10 to the minus 40th seconds and so forth, the entire universe was filled with a hot glow so intense that atoms could not form. And we see here, this is, right here, is 1 year. 10 to the 0 is 1 year, and here we are at 14 billion years. So let's compare this temperature map with what we can do to explore what is the physics like at these temperatures. I last week mentioned, I think briefly, the Nuclear Research Center in Geneva called CERN, that's the European Center for Nuclear Research. Their collider, their proton collider, can produce temperatures like this. And that's the situation that occurred in the universe a microsecond after the Big Bang. So 10 to the 13th kelvins. Another guidepost would be, what's the temperature inside the sun? This is where we were about a year after the Big Bang, 3 million Kelvin. And the whole universe was filled with that kind of temperature. And here's the point of what's called the temperature of recombination. At this point, atoms can form. So this is about less than 1 million years after the Big Bang. This is where we get this number of about 340,000 years after the Big Bang. The temperature had dropped to a point of about 3,000 Kelvin. And here we are today. By the way, here's the city of Geneva. And if you look closely, there's a human inside one of the experiments at CERN. Everything at CERN is big. Well, we're going to talk about that as well. Here's CERN on the outskirts of Geneva. So let's talk about Big Bang nucleosynthesis. So this is part of that drawing we just had for the history of the universe. There's the Big Bang. And we have no idea what went on before the Big Bang. You can pick your own idea about why we have a universe at all. And right after the Big Bang, all that existed were photons. That is the electromagnetic radiation that I mentioned is at such a high temperature that atoms could not form. And we had electrons, and we had fragments of nucleons. Nucleons are neutrons and protons. So we just had a soup of subatomic particles right after the Big Bang. Gradually, the temperature cooled, the universe got bigger. That's what this line is supposed to represent, the size of the universe. It's supposed to match this envelope that's in this drawing done by NASA. After a time, we had photons still, but we had helium and hydrogen and subatomic particles. To get to that point, that took 380,000 years. And then we have this dark age period shown here and here, in which stars form. These white dots represent the stars and that gradually gathered together under the influence of gravity to form galaxies. So we should talk about the galactic formation. Gravity did this work. Gravity is the weakest force we know of in physics. And yet, if you just leave objects out in empty space, they will be drawn together by the influence of gravity, because gravity never gets tired. It's constantly at work drawing things together. So we have the formation of galaxies near the end of the Dark Ages. That took 400 million years. And then we have expansion and cooling. Let me take a quick break and take a look because it looks like we have. Oh, have people having trouble?
Yeah, some people are saying that they can't see. I would say maybe try to unshare your screen and then share it again if you're able to,
Oh, okay.
just to see if that helps.
All right, I'm going to stop sharing and I'm going to reshare PowerPoint. Let's go back. We were doing this. Do the people who can't see?
I can see it fine. To anyone that can't see it, maybe try exiting the meeting and coming back in. Um, I'm not sure why people
Hmm.
can't see it.
It doesn't
It's
seem like everybody's having problems. Yeah,
Yeah.
so
no, it's not a comprehensive problem. This is Dave, Ed. I can see it fine, so it's individual.
all right. Well, let's carry on. We have roughly 40 people in the and only a few have had this problem. Maybe for those people, you log off and log back on, not just have me turn this sharing on and off, but log off and log back on and see if you can see the screen. So we're going to carry on. I apologize, although I have no control over what's going on there.
And one possible problem is that at the lower left of the screen, there's an audio and a video, and some people may have the video turned off. So they have to turn the video on at the lower left part of the screen.
Yeah, that's possible. Thanks, Dave. Okay, well, let's carry on with the science. I mentioned last week that when Einstein had developed his theory of gravity, the general assumption was that the universe was static, that it was perennial and was always the way it was. And it took Edwin Hubble observing distant galaxies moving away from his telescopes and George Lemaitre using Einstein's equations to show that expansion or contraction of the universe was possible. And Alexander Friedman did additional work. And so the idea began to form in the mid-1920s that the universe could be expanding and had a beginning and an evolution. Remember that Lemaitre called the beginning the primeval atom. Just thinking about the universe expanding, he thought, what happens if you run that movie in your mind backwards? You get to a single point where the whole universe was confined to a tiny volume. And so there was lots of debate, which was interrupted by World War II, about whether the universe was expanding and dynamic or was it static. And there was a vigorous debate. It wasn't until the late 1940s when research in cosmology resumed after the war that progress was really made on this. And George Gamow, a highly influential character who ultimately ended up at the University of Colorado, thought that thinking about creation of the elements in the universe could be a clue to whether the universe was eternal or was born and evolved and created elements. So he challenged his students, including Ralph Alpher, who we will talk about in a few minutes. He challenged his students to compute the abundances of atoms that should be observed by looking at the spectra of galaxies and see if the new physics of nuclear physics that evolved in the 1930s and 40s could explain the amounts of different atomic types that you observe out there in the galaxies. And Alpher and his colleague Robert Herman got busy and they did the calculations essentially by hand. Remember, no computers at that time, and the calculations are very complex. So Alpher and Herman did calculations, and they found that Gamow was wrong. Gamow had assumed that all the elements were made in the early universe. And the key to the discovery made by Alpher and Herman was that there's not enough neutrons around to create all the elements, meaning the light elements like hydrogen and helium, heavier elements like the metals and so forth. There weren't enough of neutrons around, and there's 3 reasons. First of all, if you have neutrons outside the nucleus, they are radioactive, they're unstable, and they decay in roughly 10 minutes into a proton, a weird particle called a neutrino, and so forth. So if you have a bottle of neutrons every 10 minutes or so, you have half as many neutrons. So the number of neutrons present to help form the nuclei of atomic elements in the early universe was limited by the fact that neutrons decay in a matter of minutes. Secondly, the universe was expanding. So the neutrons created in the Big Bang, suddenly you're getting farther and farther apart as the universe expanded. Now, this is true of any kind of gas. If you expand a container that has gas, the pressure in the gas goes down. So the density of neutrons available to form atoms was being reduced by the volume of the expanding universe. Third, every time a neutron found its way into the nucleus of an atom, it was removed from the cloud of neutrons that were trying to make atoms. So the more atoms that were created, the fewer neutrons were available to continue that process. And so it wasn't enough time in the early universe to create all the elements at once. And this was a mystery for a long time until the physics of stellar evolution was understood in the 1960s, and people realized heavier elements are created in the stars, not in the original Big Bang. Now, one tremendously important offshoot from the work of Alpher and Herman was that they predicted there should be a cosmic microwave background. That is, they predicted that in an expanding universe that started from a single tiny space, there should be leftover radiation, and they predicted that radiation would be about 5 degrees above absolute zero. They made that prediction in 1948, and we'll show you some details of this in a minute. So what Gamow was trying to understand is, where did all this stuff come from? This is the whole collection of all the atoms in the periodic table as a function of the atomic number. That is essentially how massive the nucleus of these things are. So you have hydrogen and helium. You have an interesting drop here, this dip for beryllium. And by the way, this is what's observed when we look at the makeup of our solar system. And we have a similar makeup for Earth. You take all the different elements that are in Earth's structure. You see the same kind of thing. Mostly hydrogen, helium, beryllium is lower, and so forth. So this was understood in the 50s, but the mechanism for creation of these elements in the early universe was not understood until Alpher and Herman showed it wasn't all in the Big Bang. It had to happen this way. So here's a neutron decaying into a proton, and the protons can collide and produce something called deuterium. And if they collide with multiple deuteriums collide, you get an isotope of helium, helium-3, that can produce helium-4 and so forth. So you have this, and notice the arrows go in all different directions. Here are the kind of equations that Alford and Herman were working with, where you have a neutron becomes a proton and an anti-electron, now called a positron, and a neutrino, and all these things are connected. You see, here's deuterium here being produced by this process, but it also is consumed in this process to produce helium. And as I say, no computers in the late 40s. It was difficult to do this with just adding machines, basically. And what a mess. But they did the work and found neutrons did not explain this process where you have hydrogen colliding to produce this isotope of hydrogen, and an additional hydrogen nucleus comes in and you get an isotope of helium and so forth. And here's the key for understanding what these colors mean. So we now understand this process, and we can do the work to calculate what the abundances of different elements should be after the Big Bang, but resulting from the mechanisms in stars. And there's even some simple arithmetic. I'm not going to go into it here, but it just says how many protons do you need to produce a helium, and from that you can derive that there should be 3 times as much hydrogen as helium in the universe, and that's what we observe. Now here's a modern version of that work that Alford and Herman did. This is a Big Bang nucleosynthesis model. Here's time starting from 1 second after the Big Bang, and here's the abundance that you would find in the universe if you could do the work back right after the Big Bang. You'd find hydrogen, you'd find neutrons. Let's, in your mind, draw a vertical line right there. You'd have hydrogen, a little bit of helium, neutrons, and deuterium, which is an isotope of hydrogen. So that's at 1 second. And then you see that it gets complicated because various mechanisms for different elements being combined to create heavier elements are underway this whole time. And here we are at 1 minute and 1 hour. And during this first minute, we began to see helium-3 shown as purple, hydrogen-3 or tritium, an isotope of beryllium, and an isotope of lithium, all being formed. And notice this is the dynamic of neutrons because of those 3 mechanisms I was talking about. The radioactivity of neutrons causes its density to decay. Neutrons also get absorbed in creating these heavier elements. And any neutron that finds its way to the nucleus of an atom is taken out of the marketplace. So we have this precipitous drop in the density of neutrons. And we're here, right here, we have a stable array of atomic matter, and we're just 1 hour into the history of the universe. So we're very early, and here's 1 day. And if we'd be interested, well, how do these numbers compare to what we see when we go look at galaxies? I'm emphasizing here, that's neutrons, that's hydrogen. And in early days, they didn't know what, this is just a historical artifact. People called helium the Y property, but that's, if you see Y sub P, that's helium. Now, to get this kind of model to work, you have to put some parameters in. One of the parameters you have to put in is how much of the universe is in the form of atomic matter and its components. That is atoms, protons, neutrons, and the components that make up protons and neutrons. We'll talk more about those in a bit. So you have to pick a number for how much material was available to form atomic matter. And this kind of result only matches observation if you pick a density of matter of 4.5% of the energy of the universe as atomic matter or its constituents. So keep this in mind. This 4.5%. We'll see this again in a minute. There's more details on here. So we're going to remember that number, 4.5%. Now we have a different way to look at the properties of the universe. By looking at the spectra of galaxies, we can look at how much, and let me get something out of the way there, how much of the universe is hydrogen, how much is helium, how much is deuterium, here's helium-3, lithium, and so forth. And these horizontal bars represent the measurements. So if you look out into the universe, you see a density of hydrogen here and so forth. Let's see. Here is deuterium, this green bar, and these are color matched. So the green horizontal bar is the amount of deuterium we see. Pink is helium-3 and so forth. Now, we're going to run our model to see what parameters we should use so that the observations, the horizontal bars, match what the model puts out. And these curves are the output of the model. And the parameter that's most important in doing these kinds of numerical experiments is how many protons are in the universe per photon. So the early universe was filled with light. How many protons were available to build atoms? And the best match occurs right here at around 4.5%. Just like we saw on the previous page, this is a different model, and it says if you pick 4.5% for the density of protons, then the deuterium, the green curve that comes from the model, matches what we observe, the horizontal green bar right there. We get matches with helium-3, also matches. And by the way, the thickness of the bar indicates how accurately we can measure the density of various kinds of materials by looking at the spectra of galaxies. So it's deuterium. Fortunately, we have fairly precise measurements of how much deuterium exists. It's harder for helium-3, and there is a question here about lithium. The prediction of lithium doesn't match the observation. And the reason is that lithium, not only it was produced in some amount in the Big Bang, but it also is produced in stars. And so it's difficult to tease apart how much of the universe's lithium came from the Big Bang versus stars. The upshot of this is, looking at this kind of model, we also conclude that a number like 4.5% for the energy density in the universe is necessary to get our model of the nuclear physics of the production of atoms to match what we observe in galaxies. So we're beginning to build a confidence that this number 4.5% is the right number, and it's also the number we get from the cosmic microwave background. We'll talk about that some more. So here's some words to fill in. Right? That's a key point in these kinds of calculations. And we've already seen this. This is the periodic table organized by where the different elements came from. And you see hydrogen right from the Big Bang, virtually all the helium and some of the lithium coming from the Big Bang. And now we know from observations of the way stars function, we know how to assign the production of these other elements that exist in the universe to different kind of mechanisms in exploding stars and so forth. Now, we already talked about CERN as a place where fundamental research is done on subatomic particles. And here's some photos from the trip my wife and I took to CERN 10 or 12 years ago. Actually, we were there in 2012. It was 13 years ago. We were there just before they announced the discovery of the Higgs boson. You might remember that was a big deal. And CERN is an enormous complex of experiments. Each of these ellipses represents an accelerator of some kind, and some of those accelerators are used to feed this big ring. It's called the Large Hadron Collider. Started doing research in 2010, and it's 27 kilometers, about 18 miles around this ring. It's underground, and it is fed, as I say, by various kinds of facilities that, in the case of CERN, of Large Hadron Collider, produces protons. And they have two rings, one going one way, one going the other way, and they watch as those protons have head-on collisions. And they have multiple experiments. Here they are, these orange dots represent the experiments. And the reason they do that is if they're looking for a particular process in the formation of subatomic particles and their decay, they want independent groups to do this experiments to detect and analyze those processes. So they make sure those groups do not communicate until they produce a deadline, and then they can share their data, not influencing one or the other. And here's the ring. As I say, it's underground. Here's the airport in Geneva. And it's an enormous facility. They spend about $3 billion a year there doing research. Again, here's one of the experiments, and that's a human to give you some sense of scale. Everything is big at CERN. And what they're looking at is that what is called the standard model of particle physics. Early in the last week's discussion, I mentioned that we now know that the properties of the universe itself depend on the properties of the smallest things in the universe. One of the areas of research at CERN is quarks. These are components that can form and produce different subatomic particles. So you take the right mixture of quarks and you get protons or neutrons. There's other things. Here's the Higgs boson. That was a big deal back in 2012. 3 classes of electrons. We have the electron so useful to us in designing electronics, and its big brother, the muon, and its even bigger brother, the tau. And each has a weird, ghostly companion called a neutrino. And the early universe was just this stuff, all in a soup that gradually cooled, and then atoms were able to form. Here's the composition of protons in a simple way. You take 2 of these ups and a down and put them together, and that's a proton. If you take 2 downs and an up, that's a neutron. So when we have when we have radioactive decay of a neutron, it's because one of these down quarks became an up quark, and it throws off those extra particles, and we have a radioactive decay of a neutron into a proton. So what we know is Big Bang nucleosynthesis and the dynamics of nuclear physics does a good job of predicting how much of each kind of element that should exist in an expanding universe. By the time this work was done in the late 50s, the idea of a static universe was completely over. There's no explanation for the evolution of the elements in the static universe model that matches the quality of this work done with Big Bang nucleosynthesis. And what's more, the static universe does not predict a cosmic microwave background. And we're going to get into that in a second. And of course, a key result is how much of the universe is made up of atoms, 4.5%. And so now we're going to have a little interlude before we talk about the microwave background. From now until the break, we're going to talk about the influence of James Webb Space Telescope. And this is just the first detailed look at James Webb. In lecture 6, we're going to go into it in even more detail. But here's a comparison of what Hubble sees looking at a particular nebula and what James Webb sees. So now we're going to compare different telescope systems with regard to how far back in the universe they can look. Principally here, what we're comparing is the Hubble Space Telescope, shown here, and James Webb. Now, this piece of art was made before James Webb was launched, but James Webb has performed better than expected. So it's become a key element in our explorations of the cosmos. And here's the time scale, time after the Big Bang. So in this drawing, the Big Bang is over here. In many drawings, the Big Bang's on the left. You just have to be careful when you're looking at this. The Big Bang on this drawing is over here on the right, and here's 200 million, 480 million, and so forth years after the Big Bang. And here we are at 13.8 billion years after the Bang. In 1995, the director of the Space Telescope Science Institute, Bob Williams, as director, decided to use his observing time for the Hubble Space Telescope to tell the scientific staff to point the telescope at a spot on the sky where there appears to be nothing. And we see the result of that in the background of this drawing. These stars and they're galaxies. These galaxies, many of which have weird forms compared to modern galaxies. This is the original Hubble Deep Field, and it could see back to about 1.5 billion years after the Big Bang. So these were early galaxies. Remember, there were no galaxies until 400 million years after the Big Bang. And this is about 3 times later. And so this is the first picture of really ancient galaxies that we were able to take and used the Hubble telescope under Bob Williams' direction to just stare at a spot on the sky for many, many hours. And this is what they got. Then they did it again 10 years later, and they got even more detailed. These are easy to find on the internet. Just put in this title, and you'll see what Hubble Space Telescope saw, looking as far back as it could. And Hubble, I mentioned Hubble's telescope has some infrared capability, and then they did a deep field with the infrared instruments on Hubble. And this is at a time when Hubble had been serviced by astronauts multiple times, and many of the original instruments were replaced with more modern instruments with more capability. And so they have even a deeper look back to 480 million years. So we're looking into the early universe when we do this kind of infrared. James Webb now is probing back to this level. And there are remnants of, or the appearance of, ancient, very early galaxies back here at these kinds of Z values. Remember, Z tells us how much redshift has occurred. The bigger the Z, the farther back we're looking. So this is kind of the history of space telescopes looking deep into the early universe. Now let's compare Hubble and James Webb in terms of the wavelengths at which they operate. Here's the visible spectrum that we all enjoy, from blue to red. And Hubble, you can see this kind of triangle, tells you Hubble can see into the ultraviolet at this end, and it can see just into the infrared at this end. So this bar represents the ability of the Hubble Space Telescope looking at different spectra out in the universe. James Webb has some capability in the visible, but its real value is out deep into the infrared, out to nearly this huge number, which is 30 microns. This is really far out into the infrared. And the Webb telescope can only do this because the entire telescope is cold. The orbit of the telescope and the design of the telescope are all optimized so that after the telescope was in its orbit around the sun, it cooled down just by radiating away heat and was insulated. The telescope itself is insulated from all the engineering, the spacecraft engineering behind that, so that the telescope is as cold as it can possibly be, and that allows it to see out here. Hubble telescope is in orbit around Earth, and it does not get cold. Some of the instrumentation is made cold using refrigerators, but Webb is inherently cold. The mirror assemblies and everything related to the science are operating at very low temperature. And Hubble has an array of filters, color filters, kind of like you would use on your camera, or when you're put on your sunglasses, it changes the spectrum that you can see. And you'll see here's a human vision right there. All these filters are part of the ability of the Webb telescope to pick color channels that were decided ahead of time by the scientific community to make sure that we could tease out what's going on in galaxies, so that we could create spectra to identify different species of atoms and to measure redshift. So here's human vision, and virtually all of the Hubble performance is in infrared channels or infrared wavelengths humans can't see. So this drawing goes out to 5 microns, well into the infrared. And then there's a different instrument that goes out to 30 microns, way into the infrared, and has its own filters. Now we can get into, let me check the time, we can get into some of the science that gets teased out from the Webb spectra. So if we look at this sample of the Webb image, there's lots of interesting things here. One of them is inside that little square is this. And by looking at the spectra of colors here and matching them against the spectra that we know from doing experiments here on Earth with different gases and materials, we can see the redshift associated with this galaxy that produced this image. And you see here the identification. If you are looking for oxygen, you need to see a big bump here and a big bump here and this kind of structure over here. These lines, these spectral lines, get redshifted into infrared wavelengths that a telescope like Webb can see. The other thing that's interesting here, you see these blobs of light, particularly this arc. These are distorted images of distant galaxies where the light has traveled near some kind of gravitational entity, usually another galaxy, and the path of that light to our telescope has been altered by what is now called gravitational lensing. This was predicted by Einstein, although in his day, he said this will never be observed, but it exists out in nature. Well, we've done the work and built the telescope so that we can actually see these distorted paths of light. That light and this light are from the same source. And here we have redshifted light in the vicinity of a Z of 30, which is just 320 million years after the Big Bang. So this is right at the end of the dark ages. These little squares produce this light and this light and this light. And in chapter or in lecture 6, I'll be talking more about these objects here, 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 and here. These are called the little red dots. And we're going to talk about why those exist and why they have their properties that they do. And what we find by using the Z value, that is how far back we're looking in time, and Friedman's equations, we can tease out some information. So this one particularly has a very high Z. That means it comes from the early universe. It's using the look back distance that first was mentioned early in this lecture. I showed the look back curve. We're talking about an object that is now 33 billion light years away from us, even though the universe is only 13.8 billion years old. Because of expansion of the universe, the distance is bigger than you might expect. And this galaxy is now 13.3 billion years old, if it still exists. We see the light as it was emitted 13.3 billion years ago. We have no light from that object since then. Here's another case, and the distance and the age. And so what I've done is I've filled in, by using Friedman's equation, I was able to fill in these look back distances and the ages of the objects on this image from Hubble. Now, here's a great way to see the comparison between what Hubble sees using visible light. Notice this cross indicates this is a deep field image from Hubble. Now I'm going to overlay on this the James Webb image of the same spot on the sky. And you can see, before I do that, here's what Hubble sees looking at this particular galaxy. And Webb, using different wavelengths, sees this structure. So we see a lot more detail. Now, let's take a look at this. I'll do this multiple times. But you'll see this kind of pattern indicates we're now looking at James Webb. And let's focus on this ellipse. See, we see structure in there. This is infrared data. Let's go backwards. This is what Hubble sees. I hope you can see it on your screen. Faint little dots, mostly visible wavelength. Now we're going to overlay what James Webb sees. All these additional galaxies that have come into view are older than the oldest galaxies that Hubble Space Telescope can see. And we also see these arcs, distorted images of, particularly this one, distorted images of a distant galaxy barely seen by Hubble. This is what the Hubble Space Telescope sees. This is what we see from James Webb. And this object is probably the massive galactic cluster that altered the path of that ancient light to produce this distorted shape here. Oh, and by the way, you can, if you go on YouTube, I think these are YouTube links, you can see additional examples. This one I did, this overlay I did, but there are others out there where people have overlaid images from Webb and Hubble, so you get a chance to see the difference. And let's focus on these a little bit. This, again, these arcs that I'm pointing to with the green arrows, they are the result of distortion by probably this galaxy or galaxy cluster changing the optical trajectory of the light coming to us. We'll have more to say about that. Let's see, let's do one more and then we're going to take a break, maybe two. Now, one of the critical things about getting the age of these objects is to have spectra. For example, this is from James Webb. That little streak spread out in spectra by an instrument on the spacecraft produces this spectrum. And we know this hydrogen-oxygen spectrum in the laboratory wavelengths, and we can use this spectrum from the spacecraft to get the redshift, the same in this case. Right there, we spread that out, and there's color lines in there, and we see the spectra we need that to get the redshift to get all this other information. One of the interesting spots on the sky that Webb has looked at is the location of the merger of two neutron stars. And in that merger, the element tellurium was created. And if you look at, well, this is the spectrum produced, this white line is the spectrum produced by the James Webb Space Telescope. And here's a model of what you would expect to see if you have a sample of tellurium and study it with a spectrometer and a redshift. Turns out this was not that far away. This is my handwriting. Calculating the redshift value is rather small, which means the speed of this event away from us is not huge. And you see the comparison. The orange line matches with the white line, and we can detect particular atomic species out there in the universe. All right, we're going to stop at this point. We're going to take a break so I can get something to drink. And we'll be back. Let's see, right now it's exactly 2. So let's come back at 2:01. Let's come back at 2:05. And we need to pick up the pace a little bit because there's 80 charts in this package and we've done less than half. So I'll see you in 5 minutes. Okay, I'm back. Let's resume. Couple of things. Keep me informed if we have any more trouble with presentation. Kevin Miller pointed out that I could just announce the page numbers. People could follow along. Also, apparently, I said something wrong early. In the decay of neutrons, you get a neutron has no electric charge. You get a proton and an electron. I might have said a positron. So the decay of the neutron produces a proton, an electron, and a neutrino. All right, well, let's resume. I want everybody to also understand the James Webb Space Telescope was not the first telescope to operate in the infrared. I mean, astronomers have known since early days that if they wanted to see high redshift objects like ancient galaxies, you need to operate in the infrared. And the best place to do it is in space, because there's some parts of the infrared spectrum that do not propagate well through the atmosphere. Although ground-based infrared astronomy is a important component of our research toolkit. Nonetheless, long ago, people started thinking about how to build infrared telescopes for space. And one of the big problems was how to keep the telescope cold. So this meant launching containers of liquid helium and so forth. It was very complicated. But people persisted because it's an important source of information about the universe. So let's compare a couple of early versions of infrared telescopes. Here's the WISE telescope from 2009, operating at around 5 microns, which is way out of the spectrum of that we can see, but it's not nearly as far out into the infrared as James Webb. Nonetheless, looking at a particular spot on the sky, WISE was able to take a picture like this. Later, actually earlier, the Spitzer telescope, operating at a longer wavelength and a larger aperture, looking at the same spot, saw this. And here's what we get from James Webb, operating at almost 8 microns. And this is a comparison of these 3 telescopes. The big circle is the Webb at 6.5 meters. And then you have the Spitzer here, that big, and the WISE is that big. So you need aperture. Bigger is better in telescopes for a couple of reasons. One is you get better angular resolution. You can tease out much more detailed imagery with a big telescope. And a big telescope collects more light. If you double the size of your telescope, you get 4 times as much light collection. So you can you can create the same image in a shorter period of time and cover more of the sky, or you can do more sophisticated things with a bigger telescope, like do spectroscopy. That is, tease the colors out so that you can measure redshift and constituent elements. Here's another example of the Spitzer telescope. Took this image, and James Webb gets much, much more detail. And this is not, infrared's not the only place to get information. Here's an example of X-ray spectroscopy looking at a particular object. And you see, again, by identifying these peaks, we can say, oh, there's silicon here, and there's sulfur and argon and calcium and iron. So we can do spectroscopy from this collaboration between the US and Japan. Now we come to the mother lode of information, and that's the cosmic microwave background. This is, as I mentioned, predicted by Ganoff's students in the late 1940s. And we're going to go through that history. It's really important. There's Ralph Alpher. I actually met him once. His brother married my aunt or something. Somehow we met at a wedding, and I was amazed to be in the presence of this guy who's a real pioneer who didn't get enough credit for his work in cosmology in the early days of modern cosmology, the late 40s. But we'll talk about that. So one of the most influential papers he wrote ended up with three authors: Ralph Alpher, Hans Bethe, who eventually won a Nobel Prize, and the famous George Gamow. And this was a result of Gamow, who was a jokester and was amused by little things. He was Alpher's thesis advisor, and Alpher had written this paper concerning evolution of elements in the early universe. And Gamow thought it would be fun to add Hans Bethe, who was famous, and himself, because this mimics the first three letters of the Greek alphabet, Alpha, Beta, and Gamma. And the paper came out with those three as the authors, even though Alpher, the student, did all the work. But it was generally assumed that Alpher was added to make this joke about Alpha, Beta, Gamma. And it really was detrimental to Alpher's career to be thought that he was just added as an afterthought. In fact, it was his work, and he was bitter about it his entire life. And in the paper, he talks about how hydrogen and helium must have been created in the Big Bang. I mean, he was the first to really see how this could all fit together and that there should be a cosmic microwave background. Luckily, he was awarded the Medal of Science by George Bush right before he died, but it's a cautionary tale about the relationship between students and the faculty that they are under, and he should not have been treated that way. Here's the famous paper. And this is pioneering work. Nobody had done anything like this until Alpher came along. There's Gamow and Hans Bethe. So here's a page from a paper by Alpher and his colleague, another student, Hermann. And if you read into this, we should be able to see a background radiation around 5 degrees above absolute zero. This is the first prediction of an afterglow from the Big Bang. We now call that afterglow the cosmic microwave background. And it took another 15 years. Oh, well, let's talk about what this means. All of physics includes the science of black body radiation. Every object radiates heat. Some of it is detectable. If you stand next to a fireplace, you get warmed by the heat radiating from the burning wood. And that heat can be described with a famous black body curve discovered in 1900. Its discovery started the quantum age. And if you take my class on quantum physics, you can get all the detail you want about how that happened and why it's important. But you see, this curve is in the visible spectrum. If you're looking at a hot body like the sun has its peak emission in color in the visible spectrum of the human eye. That's not an accident. Of course, our eye adapted over hundreds of millions of years to be sensitive to sunlight. And a cooler object, a 3000 Kelvin object, like a ember in a fireplace, has some output in the visible spectrum. So you see a red glow. And This function also describes how the cosmic microwave background behaves. And here is a depiction of the spectrum of the cosmic microwave background at 2.725 centigrade degrees above absolute zero. And the peak is in the microwave spectrum. That's what this indicates. And that's what Alpher was talking about when he said we might see a remnant glow of the Big Bang at 5 kelvins. Turns out he was very close, 2.7. But it took 15 years from the late 40s until 1964 for this afterglow of the Big Bang to actually be seen. And it was an accident. Many of you are familiar with the idea that the Bell Telephone Company had the monopoly for telephone service in the United States up until the early 1980s. And they had a laboratory in New Jersey, and they were experimenting with, for a time, with using microwave signals to carry long-distance telephone calls. And these two astronomers, both of them had a background in astronomy, were asked to build and optimize a radio telescope looking at the sky. If you could see the front of this, you see it's like a sugar scoop. The front, looking from the left here, is open. So radiation from the sky can go in and get processed in science instruments here. And they discovered that they were working on this long distance relay system until people lost interest and undersea cables started being used for long distance intercontinental phone calls and so forth. But they carried out research and discovered no matter where they pointed this thing, they got a signal. And they just couldn't get rid of the signal. There's all sorts of interesting stories about efforts they made to clean the interior of their sugar scoop, and involved hiring somebody who was fairly small to climb into this area here and clean out pigeon droppings. They thought for a while that was the source of the trouble. But happily, the Bell Telephone Laboratory was in Holmdel, New Jersey, not far from Princeton University. And this guy, Robert Dicke, was one of the early pioneers in trying to modernize our view of cosmology. And he had a small group working on these topics, and they would do seminars. Once a week, somebody would give a talk. A staff member from Bell Telephone took the drive, it takes an hour to drive over there, and attended one of these conferences and realized that Dicke was looking for a signal related to Ralph Alpher's prediction of an afterglow from the Big Bang. Here's some language from the paper that Dicke wrote, quoting that Penzias and Wilson may have found this because wherever they point their microwave antenna, they get a signal. And they tried everything to get rid of the signal, and they couldn't. And over time, people got interested in flying a spacecraft to find the cosmic microwave background. The spacecraft that was created, the Cosmic Origins Background Explorer, was launched in 1989. So we had another delay, about 20 years, to get a microwave sensor into space to look for this signal. And this is what was shown at a meeting of the American Astronomical Society. Based on the first 9 minutes of observations from this spacecraft, they drew this curve, and you might see a resemblance between this and the black body curves that I showed you a few minutes ago. The universe has produced a perfect black body. The squares are measurements, by the way. At 2.7 Kelvin, this is what Ralph Alpher predicted. And they tell me that when John Mather, one of the science leads for this spacecraft, showed this image at the meeting, the whole audience stood up and cheered because they had the first tangible evidence that the universe has a beginning And we can see the remnant of that beginning in this black body curve. There's John Mather and his colleague George Smoot. They won the Nobel Prize for their work to build this telescope, this observation platform, and get this result. In an ethical world, Ralph Alpher would have been included with this pair. Nonetheless, we carry on. So the COBE, this pronounced COBE spacecraft, gave us the first inkling of what was going on. Now, to get the signal to tease out, you have to do some work. The first signal you get looks like this, and this shape represents a sphere. We're going to talk about this. This is a way to depict a sphere around you, where this is the left and the right, and this is the up and the down of your location. So if you look up and down and spin around, you have a sphere of light coming to you. But you have to take out the redshift that's associated with the motion of the spacecraft relative to the sphere of microwave background light that you're trying to take a picture of. Because if you're approaching something, you get the signal you get is blue shifted, and if you're retreating from it, it's red shifted. So in order to process this data, corrections had to be made for the velocity of the spacecraft around Earth, the velocity of Earth around the sun, and the velocity of the sun in its orbit around the galaxy. So when you do that correction, you get this. Then you go from this to this. But then you're influenced by microwave light sources in the Milky Way. But we know where they are. So you have to take those out. And ultimately, you get this, a view of the interior of a sphere looking in the microwave spectrum, where in this case, the red, this is false color, of course. This is in a spectrum where we cannot see the colors. The red is warmer and the deep blue is colder. And the difference between the warmest and coldest locations in this image of the sphere around us is extremely tiny. It's tinier than 1,000th of a Kelvin. So now here's the discussion of the map thing I talked about. If you want to map something, you have to decide on a scheme. Like if you use this kind of a map projection for Earth, Greenland looks much bigger than Australia. In reality, it's just the other way around. The distortion from this map comes from trying to take a sphere and project it onto a flat surface. But there's a better way to do it, and that is to do this. This is a particular projection that conserves area. This projection does not conserve area, and you get this distorted view of the size of Greenland. The next effort was to improve everything about the COBE experiment, and that led to the Wilkinson Microwave Anisotropy Probe, which launched in 2001. And here we can compare. WMAP produced this. This is before they removed the millimeter wave stellar sources in the Milky Way. So here's WMAP, lots more detail than the COBE experiment, and the experiment on the ground in New Jersey. Now you can see why I called it a sugar scoop. That produced this, the same spectrum everywhere, because their angular resolution was not good. So now we're out in space with a high performance radiometer. Actually, it's two telescopes, one looking to the left, one looking to the right. And they do a bunch of sophisticated data processing to tease out the tiny temperature variations that exist in this kind of experiment. Here's another way to look at it. This is COBE. Here's WMAP giving more detail. And then the Europeans built the best of all microwave background experiments or spacecraft, the Planck experiment. And you can see another jump in quality going from COBE to WMAP to Planck. This is the spectrum you get from Planck. Not the spectrum, but the view of the sky. And so once again, if you were an astronaut out in space and we said, I want you to take a picture of the sphere of light around you, you could look up and you could look down and take photographs and stitch them together. And then you could look to the left and spin around so that this point and this point are the same point. And by taking a series of photographs, you could build this map. And that's exactly what the Planck spacecraft did over a period of years. Here's a picture of it. It had a different orbit that provided it with the ability to produce this kind of high resolution observation of the microwave background. Here again, COBE, WMAP, and Planck. Notice from the bluest blue, the coldest that has been observed in the microwave background, to the reddest red is only 400 millionths of a Kelvin. That was a big surprise. So not only is the light on average a black body at 2.7 Kelvin, but there are little temperature variations. And the importance, the reason I'm talking about this set of experiments in this lecture on the early universe is this is the earliest light in the universe that we have. Can't see anything older than this. So we want to tease out all the information we can, and it's just loaded with information I'm going to show you. I know it's redundant, but I just want to show you again, COBE, WMAP, and Planck. This is the improvement we got with each experiment. One of the things that comes right out of this is that the spatial scale of these temperature variations is indicative of the geometry of the universe. And you need Einstein's equations for gravity to see why this is so, but the idea is for large variations, large distances between the coldest blue and warmest red, that indicates that the universe is closed. That is, that it is on a trajectory to collapse. If you see it in where the cold and warm regions are far apart, then it's an open universe with a geometry like a saddle that you'd use riding a horse. What we find, though, is the spatial scale here, when it's used in Einstein's equations to analyze how the universe is expanding, the spacing we get is this, about 1 degree between the coldest and warmest spots, and that indicates a flat universe, a flat geometry. And here's the way these are depicted. I already let the cat out of the bag last week and told you the universe is flat. How do we prove that? We can prove it with the cosmic microwave background. So what I've done is drawn, here's the Planck map of cold and dark regions. And I've put 360 tick marks here. There's 100, 200, 300, 360. And then we're going to zoom in. So this is 10 degrees. And you can see spacing from warm to cold. It's kind of sort of like a degree, but we want to be more quantitative than that. So we zoom in even farther, and the spacing here is the resolution of the Planck microwave sensor, 1/6 of a degree. There's 1 degree, and it becomes even more evident that there's kind of like an average of 1 degree spacing between this warm spot and this cold spot. And that appears all over. But there's an even better way to identify what is the actual spatial scale of the temperature variations we're seeing. And I'll show you that in a second. And here it is. Once again, this is how you would map this if you were out in space by yourself with a microwave camera. You would look up and down and spin around, and you could build this map of all the light around you. But if we process this with a mathematical technique, we get this characterization of all the data in this map is captured right here, and you see the 1 degree spacing is the most prominent spacing, but there are other bumps, and the bumps continue. There's a little bump there and a little bump there. These bumps, the height of these bumps and their placing on the angular scale of this map tell us enormous amounts of information about the universe. I already mentioned that any distribution of these fluctuations near a degree indicates a universe has a flat geometry. But there's more information here. Let's go into that. In 1998, hang on, I got to take a quick drink. Here's the estimate based on ground observations of the cosmic microwave background. This is after the COBE experiment, but 1996. Wondering, I'm just thinking about why Tegmark didn't include COBE. In any case, or is it on here? I hadn't noticed. Oh, yeah, it is. Right there, COBE, he's got these red dots. But the data at the time was better than this. So that's a little bit of mystery I hadn't noticed before. In any case, this is Tegmark, Max Tegmark's work. Different kinds of measurements made by different ground instruments and COBE. And this tells us that the structure we're getting is not indicative of a universe unless it has dark energy. And our universe, we now know, does. Here's 7 years later, the same kind of drawing, and the red curve, which matches with WMAP. There's the WMAP. Oh, I know why. Oh, let me go back. I know why these points are not matching. It's because the spatial resolution of the COBE spacecraft instruments was pretty poor. WMAP was better, and you see here it's matching a model of the universe that includes inflation and dark energy. That's what that symbol always is. But it rejects the idea of an open universe, that is a geometry that is not flat, and it rejects something called cosmic strings we don't have to go into, and it rejects a universe that doesn't have dark energy. And this better fit results from the fact that WMAP had a higher spatial resolution. It was able to see things in more detail. That was 2005. And now we have this from Planck, and it matches the model that we have using Einstein's equation and other parameters, and the fit is really good. So let's talk about that a little bit more. Here it is against again, this vertical line shows us that right away tells us we have a flat universe. And another parameter that goes into this is how much matter, how much energy of the universe is in the form of atomic matter. The best fit occurs when you get 4.5%. And remember, early in this lecture, I said we get this from Big Bang nucleosynthesis, and we get this 4.5% from measuring the concentration of different types of atomic species in galaxies. So this gives us confidence that we have multiple different ways to look at the universe, and they all say that the universe is 4.5% atomic matter. And we get this pie chart. If you don't use, I'll show you in a minute, if you don't use this pie chart, you can't get this fit for these many, many data points. And look how well they fit. And what do we have here? We have 70% dark energy, 25% dark matter. We don't know what it is. We just know that a fourth of the energy in the universe is a form of matter that does not interact with light. It interacts with itself very weakly, but it is a critical factor in the formation of galaxies, 25% unknown. So what we have here is 95% of the universe is made of stuff we can't explain. And the remaining 5% is gaseous hydrogen and helium just floating around between the galaxies and within the galaxies. And then this little tiny green slice here is stars, which make up a very small amount of the universe. And then even smaller slices here for neutrinos, and we're part of this other, because we are not stars, neutrinos. Some of us is heavy elements like iron and aluminum and so forth. But this spectrum can only match the data if you use this distribution of wedges. And we're going to go into this in a little more detail. By the way, in the early universe, things were different. This is the early universe, 13.7 billion years ago. The model tells us that neutrinos were an important factor. Here, it's like invisibly small. But a smaller universe had notice this, no dark energy. The amount of dark energy in the small universe is essentially zero because dark energy exists when the volume of space increases, it gets immediately filled by dark energy. But for an ancient universe that was physically small, there's virtually no dark energy. There was dark matter, which is now this much, and there were some atoms and photons, but this is the pie chart in the early universe. Okay, so now let's go to the details of the modeling. Here again, this is the Planck cosmic microwave background. This is the oldest light in the universe. Variations. I mean, it looks like a big difference between this very, very deep blue and red, but that's only a few parts in 100,000 in temperature. So what we're going to do is, I just showed you this curve. We're going to dig into this in more detail. And we're going to look at how we can define 6 key parameters that describe our universe using the cosmic microwave background. So this is a little more background on as time went on from left to right, how there was a combination of subatomic particles to produce atoms. So you can read that at your leisure. But let's keep the momentum going. One thing to keep in mind, though, let's back up 1 second here and get this. Sorry. There. The colder regions, these areas here, would have more density of matter than the hot regions. Cold implies condensation, and warm implies expansion. And this produced, this produced areas of denser and less dense matter in the early universe. The cold regions would have more density. The warm regions would have less density. And this, in the early universe, remember the cosmic microwave background is the oldest light we can observe. This dictated where galaxies would form, because in regions where you have, the cold regions, you have a higher concentration of matter, there's more opportunity for gravity to draw that matter together and produce high-density regions. In fact, there are sound waves in the early universe dictated by this kind of areas of dense and less dense regions. So we're going to keep that in mind. That's called baryon acoustic oscillation. And it's related to peaks in the data from the cosmic microwave background. And what we see now is, if you take a look at the microwave background and then you look at where galaxies have formed and clusters of galaxies, there's a correlation between the colder regions and the density of galaxies that we observe in the modern universe. And here's a way to look at it. Here's the cosmic microwave background. It has a very high Z. Remember, high Z means ancient, old. The Z of the microwave background is 1100. That dates back to 340,000 years after the Big Bang. And there's cold regions and warm regions. And then if you look at the gas that's floating around in space, you see a correlation between this area here, cold region, and dense amounts of gas. And if you look at where galaxies are, that they emerge from areas where there's more density of stars and gas. So there's a geometric connection between the different hot and cold regions of the microwave background and the density of galaxies we see today. Okay, so here for reference, this is the Planck microwave background. This is the best data we have. And see again, the height of these bumps and this and this and so forth, they're related to the amount of dark energy, dark matter, baryonic, which is atomic matter, the curvature of the universe, and the Hubble constant, and in a way related to how many kinds of neutrinos are in the universe. All this stuff goes into the modern model of the universe and its evolution. And this is this curve drawn in a slightly different way. If you look here, this is the spacing between these is whatever they chose. The spacing here is different and it stretches this, but this curve and this curve have the same data. And there's various subtleties here we don't have to go into, but they're the same curve. And the curve assumes that the universe has dark energy, again, using the Greek letter lambda to indicate dark energy, and cold dark matter. Cold meaning non-relativistic. These are slow-moving particles. We don't know what they are. It's just dark matter. So you will see in the literature, lambda CDM, that's the model used to analyze the Planck data. So let's do some analysis. Here's the model for different possible values of how much atomic matter is in the universe. If it's 10%, you're on this dotted line. If it's 1%, you're on this dotted line. And you can see if you put that, keep everything else the same, you get a change in the prediction of the height and position of the peaks in the cosmic microwave background. Now let's overlay what we get from the Planck data onto this and see which one is most right. Are you ready? This red curve is the measurement extracted from the Planck spacecraft, and it lands right on the 5% number. Again, focusing us on getting the same number with a little error as we got from Big Bang nucleosynthesis and the concentration of atomic material in the galaxies. So let me back this up and you'll see this again. There's the range of values you get for different concentrations of atomic matter as fractions of the entire energy of the universe, and 5% matches the Planck cosmic microwave background data. Remember that? There's that 4% again that matches from the model Big Bang nucleosynthesis. How about we look at the curvature? Now here, the model is very sensitive. The positions of the peaks are very sensitive to the curvature of the universe, whether it's open, flat, or closed. Let's fly in the data. And you see the data matches a curvature. That's what this case represents. A zero curvature universe matches the data obtained from the cosmic microwave background. That's how we know the universe has a flat geometry. How about the expansion rate of the universe? Again, the model is very sensitive to what we call the Hubble constant, which is a measure of the expansion rate of the universe at the present time. So let's put in the results, and you see this number, 0.7. Do a little arithmetic with that, and you get the Hubble constant that's close to the number we get measuring it multiple different ways. Once again, we're matching results from the cosmic microwave background with our current model of the universe, and the match is very good. How about the number of types of neutrinos? Now the model doesn't change a whole lot, but we want to explore this anyway. How many kind of neutrinos that there are there? I mentioned before the break that there are 3 kinds of electrons, and each has its companion neutrino. Let's take a look at what we get here. There's some information. And it's close to 3. The microwave background tells us there are 3 kinds of neutrinos. The interesting thing is, and there they are, there's the electron, and its big brother muon, and its even bigger brother tau, and each has its own neutrino. There's other evidence that the number of neutrinos might not be 3. It might be 4. And this, unfortunately, this model, the cosmic microwave background, does not indicate that it's much different than 3, but that's an area of research. So what we see here by looking at these kinds of examples is we have a model for the universe that matches the observed measurements of the cosmic microwave background once the data is processed. And out of that, we get specific results for the properties of our universe. That the dark matter is about 27% of the universe. The atomic matter is about 4.5%. The total is about 31%. And the Hubble constant's around 70. All this is consistent with many, and the geometry of the universe is flat, very close to flat. So we have a self-consistent description of the universe using results from the cosmic microwave background matched with results from other independent measures. The data from the cosmic microwave background matches the Big Bang nucleosynthesis model quite well. So here are the Nobel Prizes for microwave background. Penzias and Wilson for their experiment. And you could have put Ralph Alpher in there, or you could have put him in with Mather and Smoot. Nonetheless, the whole science community knows about Alpher and the fact that he was abused by his thesis advisor. Now, we have to complete the story. Here's the microwave background, the cosmic microwave background. This is its brightness as a function of wavelength. But there are other backgrounds in the universe. There's optical, there's infrared. This is light that was produced by mechanisms other than stars. It's the result of, in the X-ray spectrum, certain kinds of high magnetic field behavior in galaxies that produced X-rays. And there's a background there, but we've only really explored this one. So there's more work to be done to explore these other backgrounds that may reveal additional information about the structure of the cosmos. There is some background data from the radio spectrum way down here, but the biggest window we have is this microwave background that we've been talking about. Now, here's an example of the radio background that has been explored by a scientific instrument in the desert of Australia. It's in a region that is a radio quiet zone. That is, you can't bring cell phones and a variety of other devices in there because this thing, it's about the size of a picnic table. is set on a mesh of copper. You can see here in the middle of a flat area, and it's looking at the sky, and the wavelength at which it operates can be changed a little bit. And it's looking for evidence of the radio frequency background as opposed to the cosmic background. Because stars created early in the universe could affect the behavior of the cosmic microwave background, and they're trying to detect this effect here. This is called edges, and there's some detail here what they're trying to do. Now, this comes from a conjecture by these four people, including Max Tegmark. We already talked about him. They said that in the early universe, the first stars that emerged would have X-ray emission that could alter how the gas in the universe behaved, because you shine X-rays on a gas, you ionize it, change its energy values. So they drew this curve speculating about how the universe, the light in the universe, would be altered by the emergence of stars. And in this case, the Big Bang is on the left and cosmic time is on the right. So they drew this notionally, saying if there were galaxies here, we should expect to see a dip in the spectrum at around this frequency. See this frequency. And the measurements have been made by edges out in the desert in Australia. And this is what they got. Not exactly what was predicted, but pretty darn close. And I'm happy to report that my wife, who's shown here talking to Max Tegmark, probably was the inspiration for their work. I'm kidding, of course, but anyway, we met Max Tegmark on a cruise, and they had this intense conversation about the emergence of stars at very early times. That's what this implies, that the universe was not dark for 400 million years, but rather there were stars emerging in this very early time, 180 million years into the life of the universe. Now, it is also true that there's a contrary result obtained by researchers in India, and they published their work a few years ago. So this is an area of research. You have to figure out if this dip in the energy level of the cosmic microwave background is real or is an artifact of the way the experiment in Australia was done. Now, let's wrap up with what I call concordance. And here we have a result from a paper in 2010 in which the authors merged the implications of the cosmic microwave background for the amount of matter, that is dark matter and atomic matter together, and dark energy. Remember that symbol lambda is an indicator of dark energy. So where is the universe on this map of matter and dark energy? And the cosmic microwave background doesn't tell the whole story. It confines the universe to what looks like a carrot. At the same time, acoustic oscillations, remember we talked about those baryon acoustic oscillations due to sound waves in the early universe induced by areas of cold and warm radiation, produce this thing that looks like a celery. And those two things intersect somewhere in here. And we'll draw a line on this to indicate the geometry of the universe. And this diagonal line that goes from there to there is the line pertaining to a flat universe, a geometrically flat universe. So the carrot and the celery intersect here in this region, but we can confine that intersection even more by using data from supernova explosions that help calibrate the cosmic ladder that we mentioned last time and we'll talk about more in the future. So we end up with this ellipse here. This is the most probable place that the universe sits in terms of dark energy and matter. The universe is somewhere in there. All right, now let's look at more modern information. This is from 2010. More modern information from 2013 includes lensing. Remember, I showed you a bunch of galaxies whose shapes were distorted by the path they took near massive galaxies or clusters of galaxies. And that contributes to refining where the universe is in terms of propagation of light. So I've taken a small area of this and expanded it. The dashed line is still where we would expect to be if the universe has a flat geometry. And we've added lensing, the solid lines, and baryon acoustic oscillations, which come from this. And you see we are still highly likely to be in a flat universe. That's what the microwave background says. But we can look even closer. So we're zooming in on this little ellipse. And if we add if we add all this information together, the orange ellipse is this one. But it gets refined if we add this additional information that the most probable place for the universe is right there. And here I've added a scale. So you get the values of dark energy and matter that are most likely to describe our universe. And these things intersect right on the dashed line, indicating that our universe has a flat geometry. So this is the concordance that seems to describe our universe the best way we can with the data we have now. Of course, we're not done. Here's another way to look at it. We can take various galaxies and measure some property of them related to their motion. That's what this is. And there are error bars, but the values are these big dots. And the data comes from baryon acoustic oscillation, observations of quasi-stellar objects. These are the oldest galaxies in the universe. And so if we combine this one sample from a quasi-stellar object and multiple samples from baryon acoustic oscillations seen in the correspondence between the microwave background and the location of galaxies as a function of redshift. Now let's see which model of the universe most closely matches this data. And here the result. If we use a model of the universe, 30% matter and 70% dark energy, we get this green curve and it goes right through the data points. There's a couple of outliers here, a little bit here, but dramatic agreement over a wide range of ages of the universe. If you chose a 50-50 split, you're not even close to matching the data. 40-60, not close, and 20-80, not close. So the model we have for this kind of display of data is very sensitive to the numbers you use for the amount of matter and dark energy in the universe. And then one that works is the one we get from this concordance, 69% and 31%. And that's basically what we have here, 30 and 70. So we're out of time for today. And we've covered the important details about the early universe. So thanks for sticking with me. And maybe we'll have time in a later lecture that goes quicker We can talk about the concept of inflation in the early universe, but we're not going to do that today. So I wish you well, and I'll see you next week for more on cosmology.
Thanks, Ed.
Okay, thanks for joining.
Thank you.
Thanks, Ed. Enjoyed it.
Okay,
Very
good.
much.
Thank you.
Ed, do you have your questions and everything?
Give me 1 second here.
Yep.
I'm copying. I don't think you can, unfortunately, I don't think you can copy with the chat box. Let me just see if it.
I think you can. I think you just
Oh,
have
yeah,
to do it.
yeah, it worked.
Okay. Good.
Great. Excellent. Yes, I have the questions, and as soon as you end the session, I will see, I hope, that I've been recording successfully.
I
So,
think you have.
okay, I'm going to stop sharing. Hi, Dave.
Hi, Ed. One of my requests was if you, I'm signed up for both of your courses again, because I find them so incredibly interesting and the presentation so accomplished. But if you have your latest quote unquote electronic books of both courses, if you could send me the emails with attachments, I'd
Yes.
really appreciate it.
Okay, great. I'll do that. Okay,
Thanks.
I think we're done.
Yeah, leave right now. See you next
Okay.